This is a video from section 4.8 in linear algebra. Let's take a look at 33. Prove that the row vectors of an invertible matrix A is a basis for Rn. Let A equal the matrix whose first row is A11, A12 through A1n. The second row is A21, A22 through A2n. And then we keep going. And then the nth row is AN1, AN2 through ANn. A is an n by n matrix, and remember, we're assuming A is invertible. So we start there. Assume A is invertible, and so there's a theorem back in chapter 1 that says if A is invertible, A transpose is invertible. We want to show the row vectors of A form a basis for Rn. The row vectors of A correspond to the column vectors of A transpose. So we will show the column vectors of A transpose form a basis for Rn. First, we will show the column vectors of A transpose form a linearly independent set. How do we do that? We're going to take C1 times A11, A12 through A1n, that column vector, plus C2 times the column vector A21, A22 through A2n, plus all the way through until Cn times the column vector AN1, AN2 through ANn. Okay, and we're going to set that equal to the zero vector. And so I'm going to equate entries. So in other words, I'm going to take C1 times A11 plus C2 times A21 plus all the way through until Cn times AN1, and I'm going to set that equal to 0. Then I'm going to take C1 A12 plus C2 A22 plus all the way through until Cn AN2 and set that equal to 0. And I'm going to keep going until I get to C1 A1n plus C2 A2n plus all the way through until Cn ANn, and that's equal to 0. So notice how we have a system of equations, right? Now, what do we do from there? I'm going to write this as a matrix equation. So I get the matrix A11, A21 through AN1. That's the first row of this matrix. A12, A22 through AN2, and then I keep going until I get to A1n, A2n through ANn, and then I'm going to multiply by the column vector C1, C2 through Cn, and I'm going to set that equal to the zero vector expressed as a column. Now remember, A transpose is equal to the matrix A11, A21 through AN1, A12, A22 through AN2, all the way through until A1n, A2n, ANn. That's A transpose. And then I'm going to let C equal the column vector C1, C2 through Cn, and then I'm going to let the zero vector equal the column vector, and again, this column vector is n by 1, whose entries are all zeros. So that's my zero vector. A transpose is invertible, okay? So by the equivalence theorem, the only solution to A transpose times C equals 0 is when C is the zero vector, okay? And if we're not sure, when in doubt, right, let's come back. Now remember, there's no choice. If I take and multiply both sides by the inverse of A transpose, right? So I'm going to take the inverse of A transpose times A transpose C, and that's equal to the zero vector, right? And then if I take the inverse of A transpose and multiply by A transpose, that's equal to the identity. Do you agree? So this is essentially the identity matrix times C equals 0. And so C has no choice but to be the 0 vector. But the equivalence theorem immediately gives me that, okay? That the only solution to this matrix equation is the trivial solution. And that is equivalent to saying that C1, C2 through Cn are all 0. Now, what does that tell me? The column vectors of A transpose are linearly independent. And remember that the column vectors of A transpose correspond to the row vectors of A. So the row vectors of A are linearly independent. Now remember, we need to state this. There are n row vectors of A, and the dimension of Rn is n. Do we agree? Let me say it again. There are n row vectors of A that we have verified are linearly independent. Okay? And so, additionally, the dimension of Rn is n, and so we'll see it here. The row vectors of A form a basis for Rn. And that'll do it for this video for section 4.8. And in this video, we looked at problem number 33. Okay, thank you.